Hello, everybody, and welcome back. Welcome again to question number 8 on our 1968 Ontario Senior Math paper. Okay, so we got 3 parts here, A, B, and C. We got a nice, interesting little diagram here involving a pentagon and a pentagram, I guess, but we'll get to that. A part, they want us to, prove another trig identity. I thought we had enough of that with the last question, but so this is the triple angle formula. Sine 3a is 3 sine a minus 4 sine cubed a. Okay, so this is sort of a standard one, although off the top of my head, I don't remember the solution. I need to break it down into sine a's. So sine 3a, well, I know the sine angle sum formula. It's 2 sine alpha. Oh, sorry, no, that's if we doubled it. We get sine alpha cos beta plus sine beta cos alpha. So when it comes to sine 3a, I suppose I could write it as sine a plus 2a. And then that would be sine A cos 2a. There's a double angle formula we can use there. Sine 2a, another double angle formula can be used there. And then a cos A. Now, I don't want a cos A. I don't want a cos 2a either, if I can help it. So where to go from there? Well, let's get rid of this cos 2a and trade it for something involving sines. So let's say 1 minus 2 sine squared a. And this sine 2a is 2 sine a cos a. And those cos a's will actually combine, so let's do that now. Into a cos squared a. Now that cos squared a can be changed. Expand this first a little bit, and then we get 2 sine a, 1 minus sine squared a. So that'll be sine a minus 2 sine cubed a. So we've got all the ingredients, plus 2 sine a minus 2 sine cubed a. Yeah, there we go. So we got 3 sine a's minus 4 sine cubed a's. All right, there we go. So there's your proof. There's part A. That's going to be a couple marks. Probably 3 at most, I would guess. Well, actually, I don't know the marking scheme. I don't know if these... I assume they're all worth 10 marks, because that's how the Euclid works. Although it's not how the Descartes worked, I believe. I think it was more like the Pascal-Killian Fermat, so earlier questions had less marks associated to them. Anyway, what do we got for B? Deduce the value of sine of 18 degrees. Okay. So sine of 18 degrees, I assume if you do a lot, and I do mean a lot of math, you probably know sine 18 degrees, because it's an angle that might pop up. I don't know it off the top of my head. Maybe I need to use this, although that would be sine of... I don't know sine of 6 degrees, so I don't know how that's going to help me. Maybe I don't necessarily have to use A. Maybe they're just throwing trig things at me. So sine 18. So sine 36, I don't know that. 54, I don't know that. 72, 90. 5 times 18 is 90. So that's interesting. Maybe let theta be 18 degrees. 5 times theta is 90 degrees. Now, I know sine 90 degrees is 1. And I know there is a formula for sine 5 theta, not unlike the one we just worked out for sine 3a, but it would involve a quintic, and I get a polynomial in terms of sine theta. So I'd get a polynomial in terms of my sine 18 degrees, but whether or not I could solve that quintic, I don't think so. So we're going to have to be a bit more clever. Maybe we don't jump straight to that. If I use the 3 theta and a 2 theta, I can make 5 theta. Whether or not this helps, I'm not entirely sure. Because that would at least break it, because I know how to work with 2 thetas, I know how to work with 3 thetas, so... maybe sine 5 theta and break it up into sine 3 theta plus 2 theta? And that would be sine 3 theta, which I have a formula for, cos 2 theta, which we'd have a formula for, plus cos 3 theta, sine 2 theta. We can get a formula for cos 3 theta. That's certainly possible. Another thing to realize, if 5 theta is 90, then these are complementary angles. And so the sine of this 3 theta is the cosine of this 2 theta, or, the sine of this 2 theta is the cosine of this 3 theta. It might be a good idea, just in case we end up pursuing this, to maybe make a little detour now and figure out the cos 3a formula. I mean, A part maybe hints that we don't need it, or maybe A part was there because we need this one and they want to hint at it without telling us. I don't know. So I'll get cos A, cos 2a minus sine A, sine 2a. That's how that formula works. And the cos 2a, I will change it to 2 cos a minus 1. And the sine a there, we'll change 2 sine a cos a. So we'll get 2 sine a squared. 2 cos squared a minus cos a. Oh, sorry, this should be cos cubed. Minus 2, 1 minus cos squared a. Cos a. So 2 cos cubed a minus cos a minus 2 cos a plus 2 cos cubed a. And look at that, it's almost the same thing as the one for sine. So we got that. What actually should we do? So I want sine of theta. I would like very much to be able to solve for that easily. So do I want to put it in a cubic? Maybe. Let's try 2 theta plus 3 theta is 90. So cos 2 theta is the same as sine 3 theta. Cos 2 theta is 1 minus 2 sine squared theta. And then by part A, maybe I don't need the formula I just worked out with cos 3 theta. I don't know. Better safe than sorry. So 3 sine theta minus 4 sine cubed theta. Just bring it all over to the other side. So 1 minus 3 sine theta minus 2 sine squared theta plus 4 sine cubed theta equals 0. But that's a cubic, and I don't know how to solve that cubic. I don't have the cubic formula memorized. And I'm not seeing anything that sort of immediately factors here to help me out. So I think what I'd like is perhaps to have a quadratic in sine at most would be nice. So can we do that? I don't think flipping it around the other way would work any better, but let's explore that for a moment. So it's 2 sine theta cos theta. And then we had, what was it? 4 cos cubed minus 3, no, not sine, 3 cos. Oh, but I can divide by cos theta on both sides. Oh, so this does work out nicely. Just make sure I've got it right. Yep. So now come along, divide by cos theta, because it's clearly not going to be 0. And we will get a quadratic that I can change around. So 2 sine theta is 4, 1 minus sine squared theta minus 3, right? Yeah. So 4 minus 3 is going to be 1, minus 2 sine theta, and then minus 4 sine squared theta. And now we could do a little quadratic formula. So negative b plus or minus square root of b squared minus 4ac all over 2a. Negative 8 in the bottom there is a little weird, but okay, we'll go with it. And then we get 2 plus or minus square root of 20 over negative 8. I can divide, let's say I can do 2. I can get rid of this minus sign by switching the signs up here. 20 is 2 root 5. So we can get 1 plus or minus root 5 all over 4. So one of those is sine 18. Just grab a little unit circle here. Sine 18 is going to be positive. Right, so... Oh, hold on a second. I changed to the sign there when I got rid of the minus sign. I did not change the sign of this 2 here. Well, that could have been costly. Because I was about to say it's got to be 1 plus root 5, but 1 plus root 5 would be about 3 point something, and sine 18 is going to be really, really small. But minus 1 plus 2.23 is going to be about 1 point something, divided by 4, about 0.25. So it's much smaller, and I'm expecting a very, very small angle, 18 degrees. So a very small height, a very small sine. But we'll say sine 18 is positive. So sine 18 degrees is minus 1 plus root 5 over 4. Okay, minus 1 minus root 5 over 4 would be sine of, I think, negative 72, probably. Negative 72 degrees. There we go, we got B part. We didn't use A, although I'd be curious to learn if there is a way to do this sort of complementary angle thing, but have it be sine 2 theta and cos. Because the division worked out nicely, but if I hadn't stopped and said maybe we might need this formula, I could have been stuck there for quite a while. That's not good. Okay, we got sine 18. That was B part, wasn't it? And then C, given the regular 5-pointed star shown, prove that the ratio of the perimeter of the regular pentagon FGHIJ to that of the regular pentagon ABCDE is 3 minus root 5 all over 2. So that's 3 minus about 2.23 all over 2. So that's going to be a small value, 1.5 something. So this one on top of this one, that makes sense. Okay. Let's draw a picture. Oops. Didn't mean to scroll down. I meant to go back to the... Oops, we're not on question 11. We're on question 8. We've got to scroll up more. So let's get a fresh sheet of paper. Now, they've been talking trig this whole question. So I'm thinking more trig. So I want the ratio of like this side to say this side. Let's explore some angles. It's a regular pentagon. So the big angles here are 108 degrees. Same with this angle here, 108 degrees. That means this is 72, this is 72. And similarly, this is 72. So we get an isosceles triangle here. And because it's regular, you'll also get isosceles here as well. This is 108, if 108 plus 72, so this has got to be 36. This has got to be 36. This is a 36, and this is a 36 as well. Okay, so let's give names to these. I'm going to call this Y, this Z, and this X. So we want the ratio X over Z. How can I possibly work that out? So I've got these two triangles, X, Y, and I've got 72, 72, 36. Notice these are all multiples of 18. Actually, 108 is a multiple of 36 as well. So I got this triangle. I also have this bigger triangle with the Z here and the Y here. So I think a little bit of sine law is in order here. We'll say by sine law, y is to 72, sine 72, as x is to sine 36, and y is to sine 36 as z is to sine 108. Let's just make sure I copied those right. Yep, y is across from the 72, x is across from the 36. It's the smaller one. Okay. So x is y sine 36. Oh, hopefully those sine 36s will cancel out. And then z is y sine 108 over sine 36. Oh, I don't think they will. So we get y sine 36 over sine 72 over y sine 108 over sine 36. The y's will cancel out. And then we sort of invert and multiply, and we get the fraction, we'll get two sine 36s up top, a sine 72, and a sine 108. Okay. Now, how can we calculate these? Well, 36 is twice 18, and I know sine 18 is -1 plus root 5 all over 2. I guess we might have to do what we did in B part and without prompting consider the cos. So can we get cos 18? Because then sine 36 is twice that. It's a shame they're not dealing with cos 36 because you can get cos of double the angle without having to know sine of your angle. You just need to know the cosine. But to use the sine double angle formula, you have to know both, and that's kind of annoying to me right now. Okay. Okay, so use the same trick as before. Let's say let theta be 18. What did we do before? We did cos 2 theta? No, it was cos 3 theta. So now let's do cos 2 theta. And sine 3 theta. But I want an expression only involving cosines. Well, okay, actually, I guess we could just use the Pythagorean identity. That might be a little easier than trying to... I don't know why I didn't think of that first. -1 plus root 5 over 2 squared, so that'll be... we'll have to have 4 over 4 minus 1 minus 2 root 5 plus 5 all over 4. 4, so we get 1 plus 5 is 6, so 4 minus 6, it'll be -2. -2 over 4 plus 2 root 5. Oh, that is supremely unhelpful because I need to know the square root of that. Or do I? I think we might be able to... Nah. I know that's got to be over 2. But I don't know the square root of this expression off the top of my head. Well, I guess we're going to have to go digging a little bit. It probably looks like something like a plus b root 5 squared. So that'd be a squared plus 2ab root 5 plus b squared. Oh, maybe I need a minus sign in here. No, that is unhelpful. I was gonna say A and B work just fine, but... And this is positive. But how can I do a squared plus... Oh, there should be a 5 here as well. A squared plus 5b squared giving me a -2. It doesn't work. So maybe it doesn't have the form that I think it does. I would have thought it did, though. Four minus 6, no, -2, that's fine. So why can't I make this expression do what I want? I've got the right identity. Pythagorean identity, cos squared 18 plus sine squared 18 should be equal to 1. Should be squared. Yeah. I don't like that. So maybe leave it as is, I guess. Unless I'm really missing something. All right, well, let's say cos 18. Cos 18 has got to be the same as sine 72. Right, because they're complementary. So that should be 2 sine 2 theta cos 2 theta. That should be 2 sine theta cos theta. And then divide by cos theta on both sides or something like that. Well, there's the same expression I had earlier. Why can't I get one with cos theta? This is indeed perplexing and annoying, but I need. Well, actually, do I? Because what we've really got, the x over z that we want, is sine, let's call it 2 theta squared, over sine 4 theta sine 6 theta. Is there something we could do to maybe expand these out and cancel some values so that things, I don't know, work out, I guess? So that would be particularly helpful. That's something to consider. Wait a minute. Oh, there's my goof. This should be a 4. And this is 16, this is 16, this is 16. 16 minus 6 is a 10. That's why we get a positive. Okay, God, that was bugging me so much. Plus a 2 root 5. And now it should be a 16. This should be a 4. And now this plus 10 should be a bit easier to work with. And we don't need the minus sign, so we can make them pluses. And we can get rid of all of this. Okay, squares that add to 10 this way. So maybe oh, hold on, let's make sure I didn't make another mistake somewhere. No, it looks like it should be 10 plus 2 root 5. All over 16, okay. So I need AB to be equal to 1, but I need A squared plus 5B squared to be equal to 10. I'm not liking that so much. Now, if A and B were both 1, I'd get 1 plus 5, which is 6. If I had something like 2.5, that wouldn't work out nicely. So I fixed one problem, but can't seem to go anywhere else with it. I should think they would have to be integers, but that's not working here. Because if it was 6, if I was left with 6, I'd be happy. But I've got a 10 there. If it was 6, A and B could both be 1, and we'd be all set. So maybe I'm back to this can't be done the way I want it to. If B is the square root of 2, that would get me 10, but then whatever A is going to cause me a problem. All right. A is root 5, B is 1. No, that's not going to help me. So yeah, I don't know. Let's go back to exploring this idea. Um, so sine 4 theta would be 2 sine 2 theta cos 2 theta. That'll get rid of at least one of the sine 36s up on top. One of those goes away, one of those goes away. I still have a sine 2 theta, but this is sine 3 of 2 theta. And we know that sine of 3 times a was sine 3 sine of a minus 4 sine cubed of a. And now I can get rid of another one of these up on top, leaving me with a 1 at the expense of that, and turning this into a 2. So that's something. So 1 over 2 cos 36, which I don't know, 3 minus 4. I'm going to change this to 1 minus cos squared 36 and see what that does. 3 minus 4 is negative 1, so this should be 4 minus 1. So 4 cos squared 36 minus 1 is what we should get down there. And that's going to be 1 over 8 cos 36. Oh, but this is cos of a double angle. Oh, okay, great. Minus 2 cos 36. But I can work out cos of 36. Ah, great. This is working good. That's 1 minus 2 sine squared of half the angle, so that'd be 18, and we know that one. There we go. Minus 1 plus root 5 over 4 this time, so don't make that mistake again. So we'll get 16, well actually it'll just need to be 8. 8 over 8 minus, this will be over 8. 1 plus 5 minus 2 root 5. So we get 2 plus 2 root 5, and he's back at it again. All over 8, let's say 1 plus root 5, all over 4. So that goes on the bottom there. So x over z is this should be cos cubed. That's my mistake there. So I guess we can just simplify this. So 8, whatever that thing I just did was, cubed, minus 2, whatever that thing was. So they were over 8, over 8. 2 plus 2 root 5, 2 plus 2 root 5. I may have to go back and double check this work. I'm not liking how big some of these numbers are and this cube and everything, but we'll roll with it. Yeah, looks like it'll be okay, I think. So the 8 and one of the 8's down there will cancel out, so we'll get 1 over, and over 64. 2 over 8, the 2 and the 8 will cancel out. And leave me with a 4, but then I'll need to multiply top and bottom by 16 to get a 64 here. And so that'll be 32. Oh, this should be 1 plus. Save myself a bunch of work, why don't I? Okay, 8. 1 plus root 5 over 4 cubed plus 2. Oh, it's minus 2, isn't it? Yeah, minus 2. 1 plus root 5 over 4. Okay, 4 cubed is 64. And the 8, I'll get something over 8. Minus 2 and 4 cancel out, but we'll need to multiply top and bottom by 4 anyway to get over 8. Okay. So there's that expression, and now 1 plus 2 root 5 plus 5. That's 6 plus 2 root 5. And I need to multiply it by itself one more time. 6 root 5, 2 root 5, and then 10. So 16 plus 8 root 5. There we go. I guess we can combine these. (16 minus 4), that's 12. 8 minus 4, that'll be 4 root 5. And the 8 can go up to the top. Divide top and bottom by 4, so we'll get 2 over 3 plus root 5. That's looking a little closer to our expression. Now they've got 2 on the bottom there. But the point is they've got an integer, so let's rationalize the denominator. 3 minus root 5 on top, 3 minus root 5 on bottom, and a 3 plus root 5 here. So that'll be 2 times 3 minus root 5. I'm not going to combine those because I'm hopefully about to cancel out the 2. And on bottom, 3 squared is 9, minus 5 squared is root 5 squared is 5. So I'll get 2 and 4. That'll leave me with just a 2 here. 3 minus root 5 over 2 as desired. Okay. So that was a wake-up call to me. I need to brush up on my trig. I wonder if there is a nice way to get sine 36, because I clearly was not able to get it on my own, no matter how much I tried, but that's okay, because this other idea here, using the a part of the question, really sort of helped me out there. Yeah, that wasn't too bad. I mean, the geometry was not a problem. I got that right away. Sine law was great, thanks to all the sines we'd done before. It was a bit of an issue starting the sine 18. I'm not going to lie about that. Maybe I should look up things like how to find sine 18s, how to find sine 15. Or sine 6. Those are some special angles that don't come up as much as you would expect, but are still important. Or at least, obviously, they were in 1968. But there we go. That's question number, gosh, it's been so long, 8. Up next, we're going to take a look at question number 9. Feel free to, if you liked this question, maybe you got this a lot faster than me. You're more than welcome to like it, or if you had a different way to do it, feel free to leave a comment down below. If you want to be kept up to date when I do contests like this or my regular contests, feel free to subscribe, but I'll leave that up to you. And I'll also leave you with just a sort of a clear image of question number 9. We'll look at that next time, but give it a try before I get there. Okay, we'll see you next video.